Hello, my name is Dr. Jason Ackerson. I'm a soil scientist at the Soil Health Institute. Today's talk will be covering a practical soil sampling for soil organic carbon stock in production agriculture. This talk is intended for CCAs, certified crop advisors, and other agronomic professionals who are interested in developing a program to measure and quantify soil carbon stocks, particularly with the aim there being to enter a voluntary carbon offset market. As I mentioned, this talk is intended for certified crop advisors. And if you're a CCA looking to get continuing education unit credits for this topic, you're in luck. Credits are free through the generous support of the Walton Family Foundation. However, you'll need to follow the URL at the bottom of this page to access those credits. So if you travel to the Soil Science Society of America website at soils.org/education, you'll be able to get access to this free CEU credits sponsored by the Walton Family Foundation. This webinar is part of a larger webinar series hosted by the Soil Health Institute and the Soil Science Society of America and sponsored by the Walton Family Foundation. Today is the first of these webinars, but there are several other topics that are likely relevant if you're interested in measuring soil organic carbon stocks. So our next webinar series will cover the components of soil carbon accounting, and then we'll have several webinar series related to the economics of soil health. And then the last two series will sort of outline some developing ways that CCAs can build value through soil health by developing a soil health consulting strategy and then leveraging their existing precision agricultural tools to manage and monitor soil health. So in today's talk, we'll have a really brief introduction to soil carbon stocks. We'll get into some of the nitty-gritty around how those stocks are calculated, and then we'll talk really about the practical aspects related to measuring soil carbon stocks around managing soil variation in your sampling design, and then our recommended approach for quantifying and measuring soil organic carbon stocks. So in the following section, we'll be discussing some of the aspects of soil carbon stocks, mainly what are they, how they relate to other agronomic variables, and really lay out the framework for what we'll be discussing in the rest of the talk. So why might you be interested in measuring soil carbon stocks? So one of the main aspects that is driving interest in soil carbon stocks right now is enrollment in ecosystem service marketplaces. So things like voluntary carbon offset markets require some sort of measuring or accounting of the soil carbon stocks. And so having a good, reliable measurement of carbon stocks is essential to enrollment in these markets. And particularly, markets are often driven by sort of two aspects around measuring stocks: baseline sampling, or quantifying what the carbon stocks are at the current point in time, and then monitoring, which would be measuring a change in carbon stock over time. And both of those require really accurate or reliable measurements of soil carbon stocks. And lastly, you might be interested in quantifying soil health. We know that soil carbon stocks and soil health are tightly linked. Higher carbon stocks are often related with healthier soils, so you might be interested in measuring carbon stocks as a larger soil health monitoring or measuring campaign. So one of the main drivers for current interest in soil carbon stocks is really this interest in carbon offset markets. And there's a lot of interest now in these marketplaces, particularly in the private sector, but also from the federal government, who's looking to invest through the Growing Climate Solutions Act in the sort of industry and infrastructure around developing these voluntary agriculturally based carbon markets. And central to that is the ability to measure and quantify soil carbon stocks. Ultimately, ecosystem service marketplaces or voluntary carbon offset marketplaces will really only be successful if every stakeholder involved in those marketplaces receives some sort of value. So that includes farmers, CCAs like yourselves, project managers, credit purchasers, the carbon exchanges, and citizens all need to be receiving some sort of benefit. And really that drives down to an individual level. But our goal today is to provide you with the sort of background scientific knowledge so you can make science-based decisions about your business and then make the individualized personal business decision about how you build value around those things. So take all of our discussion today as a broader scientific discussion, and we're trying to leave some open-ended wiggle room for you as an individual business person to make the effective business decision on how to integrate these ideas and topics into your business and your consulting work. So now that we know a little bit about what carbon stocks are and why there's so much interest in them right now, we're going to get into some of the nitty-gritty details around how to calculate or quantify one of these stocks. So essentially, in the most basic terms, a soil organic carbon stock is the mass of organic carbon present in a fixed volume of soil. So there's a couple key things here to keep in mind. The first is that we're talking only about organic carbon. So this is carbon derived primarily from plant material, but might also contain microbial biomass. And this is the sort of carbon that interacts with the atmosphere on management or agronomic timescales. The other piece to this equation is the fixed volume. We need to know that we're sampling a set volume of soil, and we'll get into why that's really important later on. So you might not be familiar with soil carbon stocks, but as a CCA, you're probably familiar with other forms of agricultural stocks. For example, you've probably dealt with something akin to a quote-unquote phosphorus stock, but haven't thought of it in the terms of a stock. So a pretty common sort of question we see in a lot of intro soil science classes or basic agronomy courses is the question of how much of any particular element is in a soil. So for example, you might be asked the question, okay, how much phosphorus in units of pounds per acre are in a field with a soil test value of 15 ppm phosphorus? So the really basic agronomy 101 calculation to quantify how much phosphorus is in a field would just be to simply multiply the value of 15 parts per million, so that's our soil test value, by a number 2 to get a value of 30 pounds per acre of phosphorus, right? So that's how much phosphorus, or P2O5, is in a given field. But where exactly does that factor of 2 come from? And this gets to the reason why these phosphorus values are really more akin to a stock than anything else. So if we think way back to our soil science or agronomy 101 classes, you've probably heard of the concept of an acre furrow slice. So that's the volume of soil that's 6 inches thick with an area of 1 acre. So remember when we first introduced carbon stocks, we talked about the amount of soil organic carbon in a fixed volume. Well, an acre furrow slice is a fixed volume. So if we assume a bulk density for the soil in an acre furrow slice, we end up with a 1 acre furrow slice is around 2 million pounds. So we multiply 2 million times 1 part per million, that's the unit of our phosphorus test, and we get our factor of 2. However, not every acre of soil weighs exactly 2 million pounds. And in fact, the weight of that acre furrow slice is dependent on the density of the soil. So here we're looking at, on the x-axis, bulk densities of various soils and their subsequent mass of acre furrow slice. And we see from a value of around 1.2, which would be pretty low, but possible in some agricultural settings, we have acre furrow slice of around 1.5 million pounds, all the way up to north of 2.5 million pounds for an extremely dense, 1.8, 1.9 gram per cubic centimeter soil. So we see that that factor of 2 is dependent on the density of the soils we're dealing with. Similarly, the mass of that acre furrow slice is also dependent on the depth of that acre furrow slice. So if we think of an acre furrow slice, instead of to 6 inches, if we calculate that out to 10 inches, we see that that mass increases significantly. So again, that factor of 2 would change if we were using a different depth increment. So to put some numbers to this, if we were considering an 8-inch acre furrow slice and we moved from a bulk density to 1.4 to 1.6, we've actually increased the mass of soil in that acre furrow slice by 14%. That's a non-trivial amount when we're thinking about concentrations of elements in the soil. So this concept of the acre furrow slice is really useful in really simple agronomic calculations, but as we've seen, the bulk density of the soil has a big impact on that. As well as soil sampling depth can really increase the amount of soil included in that acre furrow slice. So that level of precision, while maybe acceptable in basic agronomic 101 calculations, is really not of sufficient precision for soil carbon stock assessment. So as we alluded to on the last slide, when we're dealing with organic carbon stocks, we can't assume a bulk density and we need to know the sampling depth. So a really basic calculation here for soil organic carbon stocks, and this will be one of the few equations we actually show on the slide. So if you're not an equation fan, you can rest assured we won't get too into the weeds here. But essentially, we're looking to calculate that soil organic carbon stock. We need a couple measurements. The first is your organic carbon concentration, which is how much carbon is in the soil. This is what you could think of as analogous to the soil test value for carbon, right? You also need the bulk density. As we showed, changing bulk density changes the amount of soil we're dealing with. So we need to know that bulk density, and that's something we're going to have to measure in the field. Secondly, we need to know whether or not there's any coarse fragments. So if there's a lot of gravel, we need to remove that from our calculation. So we're looking at a factor here, CF, relating to our coarse fragment content and as a percentage. And then we need to know the depth, right? We need to know how deep we're measuring to. Often that's a fixed number, but knowing that depth is critical for calculating a stock. And the last term here is just a simple conversion to get all the units to play well together. So critically, this calculation of soil carbon stocks really requires three independent measurements. You need an organic carbon concentration, which, like I said, is analogous to the carbon test value. You need the bulk density, which can be really tricky to measure, as well as the coarse fragment content, which for many agricultural soils, because we're dealing with soils with low coarse fragment volume, if it's less than 2%, we can often omit that from sampling. But essentially, to measure the carbon stock, you need to measure three independent variables. So like I mentioned on the previous slide, three critical variables we need for carbon stocks: organic carbon concentrations, bulk densities, and coarse fragment contents. For most of this talk, we're going to ignore coarse fragment contents because they're not common in most agricultural soils. We're going to focus really just on those two key measurements: organic carbon concentrations and bulk density. So organic carbon concentration, as I alluded to before, is the amount of organic material in the soil in terms of its carbon, right? So this is mostly plant or animal derived material that's decayed and turned into organic matter. We're measuring the amount of carbon that's bound up into that organic matter. Critically, this value is very similar to organic matter that you might measure through loss on ignition, but those values are not interchangeable. Those loss on ignition methods that you've probably used to measure organic matter in a soil are not precise enough for entry into carbon markets or really to quantify stocks in general. Just as we showed with the acre furrow slice, some of the simplifications we make for basic agronomic calculations don't really extend when we need the precision for measuring soil organic carbon stocks. So in addition to organic carbon concentrations, we also need the bulk density of the soil, which is the mass of soil solids within a given volume. So here we're looking at a really basic, idealized version of the soil, with the white space being air-filled pores, the blue space being water-filled pores, and then the soil solids denoted by the sort of brown dots. So you'll notice there's quite a mixture of all of these things. So if we break this down, we can think about bulk density as just being each of those components separated out. So if we look at the total volume denoted by the orange dashed line, we remove all of the water and air, so those would be the white and blue sections, and we're left with just that brown mass. We weigh that mass, so the dry mass of the soil, and divide it by the volume gets us our bulk density. So the fewer pore spaces, the more mass of the soil is in that volume, the higher our bulk density. So critically, we need to know the mass of the soil solids and the volume that they contained, including any volume taken up by pores or water. So to recap, soil organic carbon stocks are the mass of organic carbon in a defined area to a specific depth. Or said another way, soil organic carbon stocks are the mass of carbon in a fixed volume of soil. Typically, to calculate soil organic carbon stocks, we need two measurements, omitting coarse fragments here, but we really need a good measurement of bulk density and organic carbon concentration. And lastly, the stocks are going to be dependent on sampling depth. As we increase our sampling depth, the volume of soil that we're measuring will change, which will ultimately impact the amount of stock that we can measure. So typically we'll fix the sampling depth with any survey, but we need to measure the bulk density or an organic carbon content within that fixed sampling depth. So we've discussed why you might be interested in measuring a soil carbon stock. We've talked about how to measure a soil carbon stock. And now we're going to get into some of the nuances related to what's the actual field approach look like to sampling that carbon stock. But before we get there, I think it's important to step back and think about what's driving the variability within a field in any soil parameter, and how do our sampling schemes need to address that variation. So by way of analogy, we're going to think about variability in soil pH within a field. So this is a map of soil pH derived from real data from a field in Illinois. So the various colors on this map indicate varying levels of pH. So the sort of light peach colors are low pH areas, and the high colors are areas of higher pH, the green colors. And we're going to just focus really basically on drawing one transect across the field. So this dashed line represents one line of variation across that field, and we're going to zoom in on that variability. So if we zoom in on the variability of pH across that field, we can graph the pH as a function of distance along that line, and that's the solid black line shown here on the graph. So the south end of the field is denoted on the left-hand side of the graph, and the north end of the field is denoted by the right-hand side of the graph. So if we follow that black line, we see that it kind of bounces around in really tight little spots, and then it has these sort of local peaks where it'll sort of peak about a third of the way through the field, and then drop down, and then it peaks up again and drops down, and then it reaches sort of another peak at the north end of the field. And critically, those small little peaks vary around the average value of that field denoted by the red line. So we can break the variability of pH along that line into sort of two pieces. We talked about the little itty bitty peaks where that pH value is just kind of bouncing around randomly. We consider that random variation, which is just sort of the noise in the larger signal about pH in that field. Similarly, if we remove that random variation, we're left with what we call systematic variation. So this is the variation in pH that's just due to underlying soil factors, right? The soil might have a little bit more limestone in it naturally, so it has a higher pH just through inherent soil variation. And when we're designing sampling schemes, we need to figure out ways of handling both of these sources of variation so that they don't interfere with our sampling program. So the good thing about soil variation is that a lot of that systemic variation or systematic variation is predictable. And soil scientists have spent the last century or more of research trying to figure out ways of understanding that variability. And one way we do that is through soil landscape models or soil maps. So in this case, we can sort of quantify or codify variability in soil properties in a systematic way across the landscape. A seasoned soil scientist or professional soil mapper will be able to tell you or predict how the soil is going to change by which portion of the landscape they're on. And we can account for that in designing a sample. So if we can predict and understand systematic variation, it's much more difficult to really get our hands on random variation. Now, random variation in soils really derives from what we call chaotic behavior, or things that are unpredictable. And that stems from a couple pieces. One is that a lot of these soils have been managed really intensely, and sometimes that management can induce a bit of variation. But more often, it's because soils are geologic materials. they're derived from natural processes that aren't necessarily always predictable. So the image you're looking at here is hopefully drives home how some geologic material can be really variable. We've got big boulders stacked next to really tiny, fine silt-sized particles. And in fact, this is material that looks much like the material underlying their soils in the Midwest. So this is glacial till coming out of the bottom of a glacier. And you see all of the jumble of variation. Well, unfortunately, most of our soils are derived from materials that have that level of variability, which makes that variation really difficult to understand and predict. But we can design sampling schemes that can account for that variability. So we talked really abstractly about these systematic and random variations in the fields and in soils, but what do they really mean for practical implications around measuring soil carbon stocks? And that really gets to how we develop sampling protocols. So just to get some vocabulary out of the way, in statistics, we often talk about sort of two bodies. The first being a population, which describes all of the individuals or all of the potential places you could make a measurement. So if we draw the analog to human populations, this might be all of the people in the United States. But it's often impractical to measure all those people or ask all of them a survey question if you're a political pollster. So we do what's called sampling, right? We take a small subset of that group. Instead of measuring or polling everybody, we talk to just a few select people. And that's what we refer to as a sample. However, when we're collecting those samples, it's really important that our samples are representative of the population. And what that means is that they have attributes that most resemble the population that they're intended to describe. And this covers all aspects of variation. So if we're talking about people in the United States, we need to have a sample that covers both men and women, probably in equal proportions. We need to cover people across different political spectrums, people of different ethnic backgrounds. We need to encapsulate all of the potential types of variation around people to get a good representative sample of Americans. And the key part of that is if your representative sample is truly representative, then when you ask those people a question, that answer will be close to what the population would say. If we draw the analog here to soil samples, if you collect a representative sample, then the average value of that representative sample will be equivalent to the average of the population. If we collect an average or representative sample of a bunch of locations in a field, it should get us the same average as that whole field. So to really drive the point home, and this applies to soil carbon stocks, but also all other forms of soil testing, that data is only useful if the results are coming from a representative sample that's representative of the field being sampled. So you wouldn't want to use data from your neighbor's field to determine fertilizer rates the same way you wouldn't want to use data from your neighbor's field to estimate your soil carbon stocks. Or we want those stocks to be estimated from representative data, which means getting into that field and making a sample. So we've talked about the different sources of variation and gone over some terminology, but how do we deal with that variation in practice? So the first piece of random variation is actually pretty simple to deal with. So again, we're looking at a zoomed in part of that pH transect we looked at earlier. So one way we can deal with random variation, and we do this all the time in soil sampling, is through composite sampling. So at each one of these arrows might be a place where I would take a soil core. And I could mix all those soil cores into one homogeneous sample and get a sample value for that. And that would be represented here by the blue line. So by taking a bunch of points, even though each of those points is impacted by that spikiness of the line, that random variation, by having enough points there, I can actually average out that random variation and get one value that's representative of this portion of the field. So easy trick for dealing with random variation is just by adding subsamples, building out a composite, and averaging out that variation. So for most CCAs, this shouldn't be a surprise, but you often deal with this sort of sampling through composite sampling, where we would take a bunch of cores, poke them in the ground, mix them up into a bucket, homogenize that soil, and spend one homogenized soil into the lab. Pretty typical of most soil sampling protocols. So you're already dealing with random variation. If you do some level of soil sampling, you might just not think about it in those terms. So some general rules of thumb for composite samples. Typically, you want to have at least 5 samples in any composite, so 5 cores going into a composite. But realistically, we want to see that number closer to 10 to 20 subsamples. And then as the area you're sampling increases, the number of subsamples should increase. So as you're sampling larger and larger portions of space, so either going from small parts of fields to bigger parts of fields, you need to collect more soil cores and mix them into a composite. So a general rule of thumb you see in a lot of literature is 1 subsample per acre. So that would be 1 soil core per acre of unit you're sampling, with a minimum of 5 cores regardless of sample size. So if you're sampling a 1 acre area, you would need at least 5 cores within that area. So we've talked about how to deal with the random variation, and that's by taking subsamples, building out a composite sample, and essentially averaging out that random variation. But we have a couple options for dealing with systematic variation. And the first one is actually just to treat it like random variation. We've done this for a long time in agricultural management, right? We just take a unit of field, it might be a whole field, and we do a whole field composite. So instead of taking soils at strategic points in the field, we randomly locate points. Each of those red circles would represent a location. We could collect a soil core, mix those all up, and we get one composite. And hopefully the number of composites is high enough that we can sort of average out the variation in the field. So our second option for dealing with systematic variation is through a sampling strategy we call stratification. So we can think about stratification as breaking up the population we're trying to measure into smaller, more manageable groups and measuring those groups independently. So if we're drawing in the analog again to human populations, if we wanted to know how everyone was voting in the United States, we might get a subset of men and ask them a question, and a subset of women and ask them questions, and then use those to infer what's going on in a larger population. So by breaking down that group into strata or smaller sampling units, we can put a little finer point on how those groups vary and get a little bit more accurate of a representation of what's going on in the population, or in the case of soils, in the field we're sampling. So fortunately, if we want to do some sort of stratification for our sampling, we've got a lot of options. But essentially what we need to do is we need to break our field into strata or units that have soil properties that are relatively similar or homogeneous within those units. So there's a lot of ways we can do this, but we really need some sort of data layer that is based on the soil variation. So a couple examples of these might include soil maps, yield maps, right? We know that yield can vary based on soil type, so often yield data is a really good map. But the goal here is to have some sort of variable that we think shows us how the soil varies in the field, and then we just need to build groups off of that variation. So I can take a map of pH for a field, for example, and break it into groups. And each of those groups or colors on this map now would represent individual soil stratas. So the green would be one strata, the blue would be one strata, and the red would be another strata. And our sampling goal would be to collect a bunch of composite samples in each of those strata. So to sample the green, we might take a series of soil cores at each of these X's and build those out into a single composite. So with that background information, let's talk a little bit about our recommended approach for sampling soil organic carbon stock. So as we mentioned at the top of the talk, we're trying to provide you with the scientific background to make the right business decision for how to effectively sample soil carbon stocks within your consulting business or CCA work. So we're going to provide a lot of guidance here, and it's up to you to figure out how best to follow that guidance. But if there's anything I can say about field work and sampling is that consistency pays off. So I often joke that I've got 3 rules for soil sampling: consistency, consistency, consistency. So as long as you're following a procedure that you implement at the same time everywhere, you're going to be better off. So we can break any recommendation around sampling into 2 buckets: the how and the where. So how to sample is really teaching us or thinking about how we manage that random variation, whereas where to sample is really telling us how do we manage or handle the systematic variation. And both of these concepts of how and where need to be handled in tandem to get a good soil sampling plan. So there are a lot of challenges for organic carbon sampling, largely that it can have quite a bit of random variation. Things like variation in crop litter or crop residue can impact organic carbon concentration measurements, as well as small things like earthworm burrows can impact things. So this image on the right is my hand next to an earthworm burrow. You can imagine if your soil core hit that dark, rich earthworm material, it'd have a much higher organic carbon concentration than if it hit the soil around it. So our general recommendation for organic carbon sampling, this is the how part of that, is to use some sort of composite sample, just like you would for typical agronomic testing. We recommend a minimum of 10 cores and up to 20 cores per composite to get a representative sample. And as with all composite samples, the more subsamples you have, you'll get better data because we're doing more averaging of that random variation. So bulk density sampling is probably something you haven't done outside of the classroom, maybe in graduate school. But to get a good bulk density sample, we need to collect a fixed volume of soil. So often that happens by inserting an instrument with a known volume and extracting all of the soil that ends up in that instrument. There are a lot of methods. We recommend using a slide hammer with a split core rig. And just a big caveat, bulk density sampling is super labor intensive. So you're going to need to figure out the right balance of labor and cost for your business. This is our recommended approach. We think it's a good balance between the amount of time spent for sampling and the amount of effort involved. So to collect a bulk density sample, here we're showing examples of a split core rig. We're going to take one of these small plastic sleeves, insert it inside our split core sampler, and hammer that into the ground using a slide hammer. That's the sort of black rubberized looking thing on top of here. And you're going to hammer that into a known depth and then gently excavate around that soil and extract that soil core of a known volume. And that will be the whole sample you'll send. So like I said, bulk density is really can be expensive to measure. It takes a lot of time to hammer that core in and dig it out. And the more time you take to get a good sample, the better off you're going to be. But there's lots of small things that can really impact bulk density measurement. So it's really important to have a good heads up field crew who's on the lookout for things. So for example, things like tire tracks or wheel ruts or end rows can really impact bulk density, where you've got a lot of machine traffic or vehicle traffic that's compacting the soil. And things like landing zones for lime applications on the right, those little things can really impact the bulk density of the soil and need to be considered while you're sampling. You definitely do not want to sample those areas, so making sure your field team is aware of that and knows how to avoid those areas. So even relatively homogeneous looking fields can have big variations in bulk density. So here we're looking at a field that's under controlled wheel traffic. And I've kind of highlighted the wheels here in my chicken scratch yellow light highlighter here, but you should see that we've got little high spots and little low spots at the different points of wheel traffic in the field. And those are reflective of changes in bulk density. So if you're in a field that has consistent traffic patterns like this, it's really important that your sampling crew is aware of that and adopts a standardized methodology. Ideally, right, they would have some idea of which is the best part of the soil to sample, but our recommendation is typically for our samplers to sample on the inter-row or the wheel track area. It tends to get a little more consistent results, but the key here is that they have a consistent methodology. So if you're sampling in the wheel track or in the inner row, always sample there. If you're sampling in the row, then you always want to make sure all of your samples are there. So a couple special considerations for bulk density. Because it's really expensive, we're only recommending that you collect one soil bulk density to go along with every soil organic carbon composite sample. So although you might be taking multiple subsamples and mixing them together for OC composite sample, we're really going to pair that to only one bulk density sample. So that means that with only one sample, the choice of sampling location is really critical. As we showed on the last couple slides, small variations can lead to big changes in bulk density, and it's important that your field crew is cognizant of that. And that gets to our next point of having a consistent protocol so that all of your field staff understands what to do under various circumstances and knows how to adjust their sampling protocol or sampling plan accordingly, making sure that if you send them out to a location and they think that the bulk density is impaired somehow, that they're empowered to actually go and move that sampling location to a more representative location. And lastly, a couple points on the actual implementation. We find that larger diameter cores tend to yield more consistent results. So if you can get a hold of a 3-inch sampler, the better. Bigger diameter means less drag on that core, means less of a chance of compaction while you're driving the core into the ground. And lastly, keep your depth increments small. So although you can often hammer a whole core all the way 0 to 30 inches into the ground, if you're measuring to 30 centimeters, we recommend that you split those depths into smaller increments. We find that somewhere around a 15 centimeter thick increment is probably the best bet. So if you're sampling to 30 centimeters, you'd need to take multiple depth increments. So we've covered the how of sampling, but just as important as how is when. Tillage and field operations, planting, those sorts of events can impact bulk density and carbon concentrations. So we recommend that you avoid sampling immediately after tillage or planting. Any of those field ops that disturb the soil are really good things you want to avoid sampling. So we recommend that you sample in fall after harvest or in spring prior to the field operations. The key here is having a consistent protocol so that if you're planning on revisiting these fields, that fall samples are always paired with fall samples. So if you're going to go out and do a sample this fall and maybe revisit a field in 4 or 5 years, you try to make sure that that sampling event also occurs in the fall. So we've talked about how, we've talked about when, and maybe the last piece is talk about where. Now, there are tons of options on how you design your sampling scheme, and this is really a big place for there to be a lot of innovation. There's a lot of room for growth and a lot of places where smart CCAs with good data skills can really do a lot of cool work here. Our general approach is to recommend a stratified random sampling approach, breaking the field up into similar soil units and sampling those units. I will make you aware, though, that a lot of times the sampling methodology is actually dictated from sort of the top down. So by a carbon credit client, someone who's interested in purchasing offsets, or a project manager who's dictating how that project's implemented, might tell you what sort of sampling scheme to do. The key here is that that methodology is documented and has to meet certain requirements in order for carbon credits to be registered. So one of the common protocols we've heard talked about a lot in regards to soil carbon stocks is the Climate Action Reserve Soil Enrichment Protocol. This is available on CAR's website. It describes their specific protocol with regards to soil sampling and has some guidance on sampling approaches and stratification. So there are other protocols outside of CAR SEP, but we're just going to talk about some of the aspects of CAR here. And a lot of these aspects port over to other protocols. So CAR dictates that you need some sort of stratification approach. They're pretty vague about what variables you use to stratify. but it is pretty ardent that you need some type of stratification. And then they also specify that sampling points need to be assigned randomly within those strata. So you can't be using some sort of grid. The points need to be generated. The locations of the sampling points need to be random. They require a minimum of 3 samples per stratum. So this would be 3 carbon concentration and bulk density samples within each stratum. And that allows you to calculate an average and a standard deviation of those samples. But again, there's a lot of leeway here on how those strata are determined. They could be based on soil properties, soil series or soil maps, landform, things like slope, or even done on a larger scale, something like a land resource region. So there's a lot of ways to develop that stratification. The key here is having multiple points within that strata and that those points are assigned randomly. So going back to our earlier example on stratification, if we wanted to implement a CAR SEP style stratification, we could use the same strata we developed earlier. So in this case, we've got 3 soil strata, and then we need to collect samples for each of those strata. So we're just going to talk about the green strata here, but the same idea would port to the blue and the red strata as well. So at each one of those X's would represent one of the samples we would need to take to get our minimum of 3 samples per strata. So at each X, we would collect 1 composite organic carbon sample and a single bulk density core. And we would do that for each of the respective stratas. So walking that sort of forward to the red strata, our second stratum, we would collect a certain number of cores or sample points at each of those axes here. We recommend that you develop some sort of fixed sampling density. So you're dedicating, we're going to do, say, 5 samples per 20 acres. So you have a fixed density of samples per stratum. So in this example, our red strata is larger than green, so it receives an additional 2 sampling locations, or excuse me, 3 sampling locations. So to summarize our discussion on a recommended sampling approach for soil organic carbon stocks, good sampling starts with a consistent protocol. So having your field team trained on the right way to collect samples, right things to avoid, is really important, and making sure that every team is implementing that program consistently is sort of foundation to having successful sampling. For organic carbon concentrations, we recommend collecting 1 composite sample. So this would be collecting multiple soil cores and mixing them into 1 composite. For bulk density, due to the labor constraints of collecting bulk density, we would recommend using a single slide hammer based sample. So a split core rig with a slide hammer would be used to collect a single core paired with each organic carbon concentration measurement. And then thinking about how to allocate those samples around a field, you really want to probably be considering some sort of stratified random sample. That stratification should be based on something related to soil variation. And again, those stratification schemes might be dictated to you by the project managers or carbon credit purchasers you're dealing with. So make sure you have a good conversation with anyone interested in your carbon project before you start going out and designing a sampling scheme to make sure it works with their protocols. So that wraps up our discussion of soil sampling for soil carbon stock assessments. I'd like to thank our sponsor, the Walton Family Foundation. They've paid for us to develop this content, as well as have provided the CEU credits available with this discussion free of charge. Again, if you'd like to get CEUs for this topic, please visit soils.org/education for more details. And again, my name is Jason Ackerson with the Soil Health Institute. If you have any questions, feel free to email me. I'm always happy to field questions from well-intentioned and thoughtful CCAs. Thank you.